Hi, I'm Bob. Today, let's learn the simple regression model. In the simple regression model, there are only two variables, the explanatory variable and the outcome variable. The explanatory variable is also called the independent variable or the regressor. The outcome variable is also called the dependent variable or the response variable. We assume the functional relationship to be linear in the form y is equal to beta 0 plus beta 1 times x plus mu. We call it the simple linear regression model. It is also known as the two-variable linear regression model. Y is the outcome variable, x is the explanatory variable, and mu is the error term. We write the relationship between x and y this way to show the causal effect of the explanatory variable x on the outcome variable y under certain conditions. The error term mu is also called the disturbance. It represents factors other than x that affect y. We cannot observe or collect those relevant variables, so we put them into the error term. If we can hold constant the unobserved relevant factors in the error term, that is, the change in the error term is 0, then x has a linear effect on y. Delta y equals beta 1 times delta x. Beta 1 is what we are usually interested in because it is explanatory variable's effect on the outcome variable. Beta 1 is called the slope parameter, while beta 0 is the intercept parameter. Let's look at an example of the simple linear regression model. I'm interested in how parents' income affects their children's future earnings. I collected adult children's hourly wages in 2017 and their parents' average annual income during their childhood. The explanatory variable is the parents' average annual income, and the outcome variable is their children's hourly wages after they grow up. You can download this dataset from the link below. It contains information on 2,736 adult children in their prime work ages from 25 to 54 years old. In the sample, the average children's hourly wage was $24, and their parents' average annual income during their childhood was around $38,000. I regress children's earnings on their parents' income. The model has no other control variables and it is in a linear form, so it is a simple linear regression model. I use the log terms of the variables. It's more appropriate here to use the log terms because they are more normally distributed than the level terms. And the log-log model is easier to interpret. The slope parameter, beta 1, measures the percentage change in the adult children's hourly wage if, in their childhood, their parents' annual income increased by 1%. I run the OLS regression. The OLS fitted equation is log hourly wage head is equal to minus 1.546 plus 0.432 times log parent income, where the intercept and slope estimates have been rounded to 3 decimals. We use the hat sign for the outcome variable to indicate it is an estimated equation. Let's interpret this equation. The intercept estimate is of little interest because it is the value of y when x is 0, but in our sample, x is the log of parents' income, which are positive with a mean of around 10. So we focus on the estimate for the slope parameter, beta 1. The estimate is 0.432, implying that on average, adult children earn 43.2% more if their parents' annual income had doubled during their childhood. Or precisely, it is an 54% increase if their parents' income had risen by 100%. I draw this fitted line based on the estimated equation. It is upward sloping. There is a positive correlation between adult children's earnings and their parents' income. It is a causal effect on the parents' income on their children's income under very strict conditions, which are usually not satisfied. So we say correlation does not necessarily mean causality. The estimate of 0.432 is the measure of intergenerational income persistence. It is a measure of the correlation in labor income between parents and children. We notice that for each xi, there is a fit value y hat I. We calculate each y hat I from the estimated equation. For each observation I in the sample, there is a residual mu hat I. The residual mu hat I equals yi minus y hat I. The residual for each observation I is the difference between the actual value yi and the fit value y hat I. We can see the actual observation points, the fitted points, and the residual in this graph. This is the actual observation point, and this is the fitted point. The residual is the vertical distance between the actual and the fitted points. This residual is positive. Some residuals are positive, some residuals are negative, such as this one. The method of ordinary least squares, OLS, is to minimize the sum of the squares of the residuals. In other words, we find a straight line that goes through the observations such that the sum of the squared residuals is the smallest. The two estimates, beta hat 1 and beta hat 0, that define the straight line are the OLS estimates. Let me show you the derivation. The residual mu I is the difference between the actual yi and the fitted value y hat I. We plug in the fitted equation for y hat I. We express the residual as a function of the beta hats. We put it into residual minimization and choose beta hats to minimize the sum of squared residuals. We have two choice variables, beta hat 1 and beta hat 0, and therefore have two first-order conditions. The first one is as follows. The first derivative with respect to beta hat 0 is equal to 0. The solution is given as equation 1. It says the estimate of intercept parameter equals the mean of the outcome variable minus the estimate of slope parameter times the mean of the explanatory variable. It links the estimates of the two parameters. The second first-order condition leads to a solution to the estimate of the slope parameter. The solution is often expressed as the sample covariance and sample variance. We use the trick to accomplish it. Now we have the OLS estimate of the slope parameter beta hat 1 and the OLS estimate of the intercept parameter beta hat 0. Beta hat 1 is the sample covariance between xi and yi divided by the sample variance of xi. Beta hat 0 relates the beta hat 1 with the sample means. We can further express the slope OLS estimate as sample correlation and sample standard deviations. It is equal to the sample correlation between xi and yi, rho xy, times the ratio of the sample standard deviation of yi to the sample standard deviation of xi. So now we understand that the slope OLS estimate in a simple regression model reflects the correlation between the two variables. Another way to derive the OLS estimates is to use the method of moments. We have two moments here, the population mean and the population covariance. The parameters beta 1 and beta 0 are related to the moments. We write the two moments in terms of the variables x and y and the unknown parameters beta 1 and beta 0. The sample counterparts are as follows. We choose estimates beta 1, 0 and beta hat 0 to solve the sample counterparts. We rewrite equation 1. It allows us to express beta hat 0 in terms of beta hat 1, the sample mean of y and the sample mean of x. We see this solution again, and it indicates that the point of the sample means is on the OLS fitting line. Dropping the 1 over n term and plugging beta hat 0's equation into equation 2, use the solution to beta hat 1. We use the same trick to write beta hat 1 as the sample covariance between x and y divided by the sample covariance of x. Using the same algebra, we can also write beta hat 1 as the sample correlation between x and y times the ratio of sample standard deviation of y to sample standard deviation of x. For the OLS estimates to represent causality between x and y, the zero conditional mean assumption must hold. It says that the average value of the error term is the same across all x. In other words, the error term mu is not correlated with the explanatory variable x. Or more precisely, the error term is mean independent of x. This assumption concerns the other unobserved factors contained in the error term mu. We assume that these unobserved factors are not related to the explanatory variable x in the sense that, given a value of x, the mean of the distributions of these unobserved factors is 0. Next, let me introduce the population regression function. The population regression function is the relationship that holds on average between x and y in the population. The error term mu represents the other factors that lead y to its actual position that differs from the fitted value based on the population regression function. Here's the illustration of the zero conditional mean assumption using our example of the intergenerational income persistence. At a given value of the log of parents' annual income, say 9, the distribution of the actual children's hourly wages is centered on the population conditional mean. Some children's wages could be higher and some lower, but on average, the mean of the distribution of the error term mu is 0. So for any given value of x, the distribution of y is centered around the population regression line. In a randomized controlled experiment, like a science experiment, subjects are randomly assigned to the treatment group and the control group. The random assignments ensures that the explanatory variable x and the error term mu are independent. That is, the unobserved characteristics and the treatment are not correlated, which implies that the conditional mean of the error term mu given the explanatory variable x is 0. So, experimental data automatically satisfy the zero conditional mean assumption. But in economic research, we usually have observational data, which is not randomly assigned. If the zero conditional mean assumption holds, the observational data look as if the experimental data, and therefore a causal relationship can be established. So the zero conditional mean assumption is crucial for estimating causality or causal effects. However, in reality, this assumption is almost always invalid. Finally, I want to introduce some useful properties of the OLS estimates and statistics. They were derived from the method of OLS, or the method of moments. They hold for any dataset and have nothing to do with the zero conditional mean assumption. As long as we employ the OLS method, the following properties are true. First, the sample mean of OLS residuals is 0. It follows immediately from the OLS first-order conditions. The OLS estimates beta hat 1 and beta hat 0 are chosen to make the residuals add up to 0. Second, the sample covariance between the explanatory variable x and the OLS residuals is 0. The proof is as follows. Third, the point of sample means is always on the OLS fitted line. We have mentioned it before. The fourth property is that the sample mean of y equals the mean of the fitted values. We can prove it. Fifth, we define the total sum of squares, the explained sum of squares, and the residual sum of squares as follows. The total sum of squares measures the total sample variation in Y. The explained sum of squares measures the sample variations in Y hat, the fit values. The residual sum of squares measures the sample variation in mu hat, the residuals. The total variation in Y can always be expressed as the sum of the explained variation and the unexplained variation. It can be proved that the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. We often use R² to summarize how well the OLS regression line fits the data. R² is the ratio of the explained variation to the total variation. It is interpreted as the fraction of the sample variation in Y that is explained by X. R² is always between 0 and 1. When interpreting R², we usually multiply it by 100 to change it into a percent. For example, in our intergenerational income persistence regression, the R² is 0.139, meaning that 13.9% of the adult children's hourly wage variation can be explained by the parents' income variation. A low R² is due to many relevant variables being omitted from the model. When we discuss the second OLS property, you may wonder how we can distinguish it from the zero conditional mean assumption for the population. The zero conditional mean assumption implies that if the explanatory variable x and the error term mu is not correlated, or their population covariance is 0, then the OLS estimates are unbiased. It is an assumption about the population. We don't know whether it's true or not. If it is true, then the OLS estimates are the unbiased estimates for the true values of the slope and the intercept. And the OLS fitted line is the true relationship between the population x and y. The second property here is about the OLS method. For any given sample, the OLS estimates have this property. It says nothing about the population or the true relationship between x and y. The true relationship could be very different from the OLS fitted line. The simple linear regression model is straightforward to interpret. However, it has its limitations. First, the functional form is linear, but the actual relationship could be nonlinear. Second, the model contains no control variables to rule out the influence of those relevant factors. The OLS estimates are biased if the zero conditional mean assumption is not true. It leads to our next course on the multiple regression models. Thank you very much for watching this video. See you. Thank you for watching this video and subscribing to my YouTube channel. See you next time.